Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine standing in this just completely dry, freezing, dusty wasteland. Like the air around you is so incredibly thin you couldn't even take a single breath.
Right, because it's mostly carbon dioxide.
Exactly. It's almost entirely carbon dioxide. And the temperature is just brutally cold. I mean, it regularly drops to minus 100 degrees Fahrenheit.
Easily, yeah.
And everywhere you look, literally spanning all the way to the horizon, there is just this endless, desolate expanse of red, oxidized rock and dust.
Just absolute desolation.
Right. So you are standing there looking out at this barren, completely silent landscape, and you are utterly unaware that directly beneath your heavy boots is the frozen ghost of a roaring ancient river.
It's such a wild concept.
Yeah.
Because, you're standing on the surface of a world that appears completely dead. It's essentially a planetary graveyard.
Yeah.
But just tens of meters below that stagnant crust lies the architecture of something incredibly dynamic. It's a profound image, I think, because it forces us to confront how much history is simply, hiding in plain sight.
Just obscured by billions of years of weathering and dust.
Exactly.
And finding that hidden architecture is precisely what we are exploring today. We are taking a journey to Mars. Specifically, we are traveling to this massive geographical feature called Jezero Crater.
Which is such a fascinating spot.
Oh, it really is. And we're doing this to uncover a truly paradigm-shifting discovery made by NASA's Perseverance rover, because we aren't just looking at the surface geology today.
And we're going deep.
We are going more than 35 meters underground, straight down through the impenetrable rock. And we're doing this to understand this profound shift in our understanding of time, of planetary evolution, and of habitability itself.
Which, it represents a staggering technological feat on its own. Yeah. Just considering we are talking about a remote-controlled laboratory operating millions of miles away.
Yeah, driving around on another planet.
Right. But more importantly, the data it sent back fundamentally rewrites the timeline of when water existed in our solar system.
Yeah.
And critically, how long it actually stayed there.
So, if you've ever wondered how scientists actually piece together these billion-year-old puzzles, today we are going to unpack exactly how we see the invisible.
It's all about reading the rocks.
Exactly. We are going to explore why finding a buried river delta in this specific Martian crater might just be the single biggest boost yet in our ongoing search for ancient life in the universe.
Because the search for life isn't just a simple matter of finding out if water ever existed on a planet. We know water is surprisingly common in the universe.
Right. There's ice everywhere out there.
Yeah, exactly. The critical factors are when the water was there, the specific chemical environment it interacted with, and most importantly, the duration of its stability.
Yeah.
How long did it stick around?
Right. So we have this massive bowl on the surface of Mars. Let's talk about the origins of Jezero Crater, because this isn't just a random shallow divot in the dirt.
Not at all. It's a colossal basin.
Located just north of the Martian equator, and it is approximately 45 kilometers in diameter.
Which is huge.
For perspective, that is about 28 miles across. Like, you could fit several major metropolitan cities inside this thing and still have plenty of room to spare.
Easily.
And the way a basin of this magnitude is formed is almost unfathomably violent.
Oh, absolutely.
Oh.
To understand that violence, we really have to rewind the clock back to the Noachian period of Martian history.
Which is when?
We're talking almost 4 billion years ago.
Wow.
Yeah. It is a time frame that honestly kind of defies human comprehension. 4 billion years ago, the solar system was an incredibly chaotic, dangerous place.
It's the shooting gallery.
Literally a shooting gallery.
Yeah.
It was filled with rogue debris left over from the formation of the planets. And during this period, a massive asteroid, likely several kilometers wide, just slammed into the Martian surface.
I can't even imagine the force of that.
The impact was a localized apocalyptic kinetic event. It displaced an immense volume of planetary crust in a fraction of a second.
Yeah.
It would have vaporized solid rock on contact.
Just instant vaporization.
Yeah, and that's what created this 45-kilometer wide scar.
So you have this singular moment of absolute blinding destruction, a transfer of energy so powerful it literally melts and reshapes the topography of an entire region.
Right.
But then, as the literal and figurative dust settles over the ensuing millions of years, that violent scar begins to serve a completely different purpose.
That's the ironic beauty of it.
Yeah.
The geometry of an impact crater of this specific size actually transforms it from a site of incredible devastation into a potential cradle for chemistry.
How so?
Well, structurally, it becomes a perfect enclosed basin. Think about it. If a planet has an active hydrological cycle, meaning rain, flowing rivers, or melting ice, that water is relentlessly going to obey gravity.
It wants to find the bottom.
It seeks the lowest possible elevation, always. So a 45-kilometer wide, multi-kilometer deep crater is a highly welcoming low point.
Just a giant bowl waiting to be filled.
Exactly. It is uniquely shaped to hold standing water, not just for a season, but for millennia.
Which naturally draws our attention to a very specific geographical zone within Jezero Crater, one that has held the fascination of geologists for years now. It's called the margin unit.
Right, the margin unit.
And it is exactly what the name implies, right? It is the geological terrain situated directly along the inner edges, the margins of the crater walls.
Yep, the inner perimeter.
And orbital satellites that were mapping Mars from space, they noticed something highly unusual about this specific ring of rock. It is absolutely packed with a mineral compound called carbonates.
And carbonates are huge. They serve as a vital geological fingerprint for us.
Why is that?
Well, because we obviously cannot physically test every rock in the universe, our entire baseline for understanding mineral formation comes from the physical chemistry of our own planet.
Right.
And on Earth, when we locate large deposits of carbonates, we know they are almost exclusively forged in stable aqueous environments.
So environments like shallow, sunlit seas or massive, tranquil lake beds.
Exactly. Because the chemistry behind it requires a very specific set of circumstances to occur.
It doesn't just happen anywhere.
No, not at all. Carbonates form when carbon dioxide gas from a planet's atmosphere dissolves into liquid water.
Okay.
That dissolved carbon dioxide then chemically reacts with various minerals that are present in the surrounding rocks. We're talking about elements like calcium or magnesium.
Right, making a new compound.
Through that chemical reaction, a completely new solid mineral is created. And then it precipitates out of the water and settles on the bottom. But the absolute critical requirement for this whole process is stability.
Meaning it takes time.
It takes a lot of time. Carbonates do not precipitate during a sudden, violent flash flood.
Right.
They don't form in a shallow puddle that just evaporates after a few Martian days. They demand a substantial body of water that sits calmly, interacting with the atmospheric and geological environment over an extended, sustained period.
You know, I've always pictured this process like a dry, ancient bathtub.
Well, that's a good way to look at it.
Yeah, like if you draw a bath, let the water sit in the tub for a really long time and then eventually drain it, you are inevitably left with that distinct ring of soap scum and hard water minerals gripping the porcelain around the edge.
Yep, the classic bathtub ring.
Right. And even when the water is completely gone and the tub has been bone dry for weeks, that bathtub ring remains as this undeniable proof of exactly where the water level used to be.
That's exactly what we're looking at.
In Jezero Crater, the margin unit is the bathtub ring. The water itself either evaporated or froze billions of years ago, but that undeniable ring of carbonates left behind, permanently etched into the inner walls of the rock, it tells you exactly the elevation where a massive, stable lake used to sit.
It really is. The carbonates are essentially the chemical memory of the lake.
I love that phrase. Chemical memory.
Yeah, they're just sitting there completely exposed to the Martian sky, providing an unambiguous historical record of standing water.
But okay, if the bathtub ring is so obvious, right? Why can't we just look at the floor of the crater to see the rest of the evidence?
Oh, well, that's the tricky part.
Right, because we know the surface geography strongly suggests a massive lake was there. But the problem is that the surface of Mars is notoriously deceptive.
It hides its secrets well.
It does. It is not a pristine museum exhibit. It has been bombarded by cosmic radiation, violently swept by planet-wide dust storms, and subjected to massive temperature fluctuations for billions of years.
Constant degradation.
And the entire planet is blanketed in this pervasive, shifting red dust, this oxidized iron that just obscures everything.
It hovers up all the fine details.
Exactly. So the massive challenge for scientists becomes, How do we actually prove the complex history of what happened beneath that ubiquitous dust?
Right.
How to look back in time when the surface layer has been aggressively scrubbed and covered up by the elements?
Because you simply cannot rely solely on surface morphology. Just looking at the shapes from orbit isn't enough.
Right, it's just the frosting on the cake.
Exactly. You have to find a way to pierce the crust. You have to analyze the stratigraphy.
And it's just the layers, right?
Yes. The distinct chronological layers of rock hidden below that chaotic weathering zone. Because while the surface is subjected to constant physical and chemical degradation, the deep subsurface operates completely differently.
It's protected.
It operates as a protected geological vault. It is shielded from the radiation and the wind, which means it preserves a pristine structural record of the planet's past.
And to unlock that geological vault, we had to send a machine that is, frankly, arguably one of the most sophisticated pieces of mobile laboratory equipment ever engineered by human hands.
Oh, without a doubt, the Perseverance rover.
Let's actually look at the parameters of this mission for a second. Perseverance was launched back in the summer of 2020.
Feels like a lifetime ago.
It does. And it eventually had to endure that terrifying, fully automated entry, descent, and landing sequence.
The 7 minutes of terror.
Yes, the 7 minutes of terror to finally touch down safely on the Martian surface in February 2021.
And it's important to remember that the rover was explicitly designed not just as a fancy camera platform.
Right, it's not just taking panoramas.
It is a robotic astrobiologist. Its primary directive is to search for the physical or chemical signatures of ancient microbial life.
And to grab samples.
Exactly, to meticulously collect core samples of the most promising rocks for an eventual return to Earth. And NASA selected Jezero Crater as the landing site precisely because of that carbonate bathtub ring you mentioned.
It was a glowing neon sign pointing them there.
It really was. All the orbital spectrometry data and the topographical models pointed to this specific basin being one of the most likely places on the entire planet to have once harbored a habitable environment.
So we dropped a nuclear-powered robotic geologist into the most promising dried-up lake bed we could find.
Basically.
And tucked inside Perseverance's extensive toolkit is the instrument responsible for this entire paradigm shift. It's an instrument called RIME-MFX.
Right, RIME-MFX.
Which stands for Radar Imager for Mars's Subsurface Experiment. And this specific tool allows the rover to peer straight down into the solid ground, penetrating to a depth of more than 35 meters.
Which is incredibly deep for this kind of remote work.
Just for a visual, 35 meters is roughly equivalent to the height of a 10-story office building.
Wow. Yeah, that's substantial.
Peering down that deep through solid rock is nearly twice as deep as any previous high-resolution radar study ever conducted within this crater.
And we have to talk about the operational methodology required to achieve this depth and clarity, because it is staggering.
It wasn't easy.
No, this data was not collected by simply parking the rover, turning on a scanner for 5 minutes, and printing out a neat little cross-section of the crust.
If only it were that simple.
Right. It required a massive, coordinated team of scientists. It was led by Emily Cardarelli at the University of California, Los Angeles.
UCLA, right.
Yeah, and she was working alongside researchers from institutions all over, including the University of Oslo and ETH Zurich. They had to painstakingly plan, execute, and analyze a highly complex series of movements.
They ultimately conducted 78 distinct individual traverses of the crater floor.
Think about that number, 78.
78 carefully planned routes, executed over a period stretching from September 2023 all the way to February 2024. That is months of driving.
And operating a rover for 78 traverses involves navigating just extreme logistical hurdles. You're dealing with a communication delay ranging from 5 to 20 minutes each way.
Depending on where the planets are.
Depending on planetary alignment, exactly. So you cannot simply drive it with a joystick like an RC car.
Right. If it falls off a cliff, you won't know for 20 minutes.
Exactly. Every single movement, every wheel rotation has to be modeled in a simulated environment on Earth first to ensure the rover doesn't get irrevocably stuck in a sand trap or, damage its suspension on a hidden boulder.
So the commands are batched up.
Yes, the commands are bashed and sent across millions of miles of empty space. And during these grueling slow-motion drives, the RIME-MFX instrument is just continuously firing radar pulses downward into the Martian dirt.
Let's actually break down the physics of ground-penetrating radar for a moment, because the instrument isn't just taking an X-ray photograph of the dirt. It's a bit more complicated than that.
It is. Ground-penetrating radar operates on the principles of electromagnetic wave propagation and reflection.
Okay.
So the RIME-MFX antenna emits a continuous series of high-frequency radio waves directed straight down into the subsurface.
Shooting waves into the ground.
Exactly. And as those electromagnetic pulses travel downward, their speed and their trajectory are entirely dictated by the physical and chemical properties of the material they are passing through.
Which makes sense.
Right. And specifically, they are affected by a property called dielectric permittivity.
Meaning, basically, that different types of rock or soil will slow the radar wave down by different amounts.
Precisely. In geology, we refer to these different rock types and formations as lithologies.
Lithologies. Okay.
So imagine you might have a layer of porous, highly compacted volcanic ash sitting directly on top of a dense, crystalline layer of basalt rock.
Two very different densities.
Right. When the descending radar wave hits that boundary, the exact interface between the two different lithologies with different densities, a portion of that electromagnetic energy is reflected.
It
bounces off the boundary and travels back up to the surface where it is detected by a receiving antenna on the rover.
So the rover is essentially driving along, shouting invisible radio waves into the ground and timing exactly how long it takes for the echo to bounce back.
That's a great way to describe it. And by measuring the precise time delay, as well as the amplitude of the returning signals, scientists can determine exactly how deep that boundary is.
And figure out what the rock is made of.
Or at least infer the density of the material, yes. And what the UCLA team found in the return data was remarkably consistent. They observed highly distinct reflection patterns.
What did that look like?
Well, layers of rock that strongly reflected the radar waves appeared as dark bands in the visual data sets, while weakly reflecting lithologies registered as light bands. So the team took this massive cache of light and dark reflection data, and they combined it with ultra-high-resolution orbital satellite imagery.
From the orbiters above.
Yeah. And then they merged all of that with the rover's exact millimeter-accurate GPS coordinates.
Which is just a crazy amount of data processing.
Oh, massive amounts. But it allowed them to construct a comprehensive, incredibly detailed 3D topographical map of the ancient hidden layers buried beneath the crater floor.
Okay, I have to pause here and channel the skepticism of the listener for a second.
Oh, please do.
Because I am picturing a team of highly educated scientists sitting in a lab, staring at a computer monitor, displaying thousands of squiggly light and dark lines.
Right.
A visual output that looks, honestly, a lot like a medical ultrasound.
It does look like that.
And if a doctor looks at an ultrasound, they know what a human baby is supposed to look like, so they can interpret the echoes. But we are looking at alien dirt. So how does a team look at a 3D map of varying rock densities and definitively declare, yes, this specific pattern of light and dark echoes proves this was an ancient river delta?
It sounds like a stretch, right?
Exactly. How do we know these aren't just, random chaotic layers of rock shattered by the initial asteroid impact? Or layers of volcanic lava that just cooled over time in weird shapes?
Well, that skepticism is entirely warranted. Honestly, it is the fundamental engine of the scientific method.
You have to ask those questions.
You do. And if the RIME-FX data had simply returned a series of flat horizontal layers or maybe just chaotic jumbled rubble, your alternative explanations would absolutely be the most logical conclusions.
Because craters and volcanoes do that.
Exactly. Impact craters generate massive amounts of flatly deposited impact melt, and volcanoes lay down vast horizontal sheets of basalt. It's very common.
Right.
But the scientists weren't just looking for the mere presence of layers. They were looking for the very specific, undeniable geometric architecture that those layers formed.
The shapes.
Yes, the shapes. The radar revealed shapes in the deep subsurface that simply do not occur through chaotic impacts or volcanic flows.
So the radar pierced the dust and found a structure that geologists refer to as clinoforms.
Yes, clinoforms. And they are the critical piece of evidence in this entire investigation. The team detailed these findings in the prestigious journal Science Advances back in March of 2026.
And to understand why this discovery is so monumental, we need to completely unpack the concept of a clinoform.
You really do.
What exactly is this shape, and why does it serve as this, smoking gun for a river?
So a clinoform is fundamentally a distinctively sloping, inclined layer of sedimentary rock.
Sloping, like a ramp.
Like a ramp, yeah. And when geologists or stratigraphers observe a repeating sequence of these specific downward sloping layers stacking against each other, the debate ends.
Really? It's that definitive?
It is. Clinoforms are the absolute, unambiguous hallmark characteristic of a prograding river delta. The mechanics of physics dictate that you cannot generate this specific geometric structure from a sudden rock slide. You can't get it from the slow cooling of a lava field or from the gradual accumulation of wind-blown Martian dust.
So the mechanism of creation is entirely dependent on the fluid dynamics of moving water.
100%. Picture a massive, active river system flowing rapidly across a terrestrial landscape.
Got it.
As that vast volume of water moves, it possesses significant kinetic energy.
It's powerful.
Very powerful. That energy allows the river to act almost like a conveyor belt, scouring the landscape and carrying a tremendous suspended load of geological material.
We're talking rocks, dirt.
Everything from heavy gravel and coarse sand all the way down to microscopic silt and mud. And as long as the river maintains its velocity, all that material stays suspended in the churning, turbulent flow.
You know, I picture it like a person sprinting full speed down a hallway while carrying this towering stack of heavy cardboard boxes.
Oh, that's a brilliant analogy.
Like, as long as they keep sprinting, their forward momentum keeps the boxes balanced against their chest.
Right.
But if they suddenly slam into a massive wall of, say, thick jello, all of their forward kinetic energy is instantly absorbed.
They'd stop dead.
They come to a dead halt, and they immediately drop everything they're carrying right there at the point of impact.
That analogy perfectly illustrates the physics of geological deposition.
Yeah.
The wall of jello, in this case, is the standing body of water.
The lake in the crater.
Exactly. The tranquil, stable lake that filled the basin of Jezero Crater. The moment that fast-moving, churning river hits the calm, still water of the lake, its velocity plummets.
So it hits the brakes.
The kinetic energy dissipates almost instantly. And because the water is no longer moving fast enough to overcome gravity, it can no longer carry its suspended load.
It drops the boxes.
It drops the boxes.
Yeah.
The heaviest, coarsest materials, so the large pebbles and the dense grains of sand, they drop out of suspension immediately, settling right at the mouth of the river.
Okay, what about the lighter stuff?
The finer, lighter materials, like the suspended mud and silt, they drift just a little further out into the deeper lake water before slowly, eventually settling to the bottom.
And as this exact process repeats continuously, day after day, century after century, for potentially millions of years, that dumped sediment really begins to stack up.
It builds out.
Right, it builds outward from the shoreline, advancing deeper into the lake, creating these distinct, angled, sloping ramps of mud and sand.
And those advancing sloping ramps are the cliniforms.
No? Okay.
So when the RMFX radar penetrated 35 meters into the darkness, it didn't just bounce off random horizontal layers of lava. The electromagnetic echoes mapped out a buried topography that perfectly matched the dynamic, sloping geometric structure of an advancing river delta.
That is incredible.
The architecture is just unmistakable to anyone trained in sedimentology.
Finding a buried river delta on another planet is a staggering achievement on its own, just mapped from the surface.
Right.
But the researchers didn't just map a shape. They applied dating models to the stratigraphy, and the study dropped an absolute bombshell regarding the timeline.
This is where it gets really crazy.
Yeah, according to the data analyzed by Cardarelli's team, this specific buried delta that Perseverance was driving over formed during a window between 3.7 billion and 4.2 billion years ago.
And the implications of pushing the timeline of Martian surface water back past the 4 billion year mark,
Yeah.
I mean, it cannot be overstated.
It changes everything.
It drastically alters our entire chronological model of the planet's evolution.
The timeline is what makes this a true paradigm shift because, and we should clarify this, we already knew there was a delta in Jezero Crater.
Right, that wasn't a secret.
Anyone with an internet connection can look at the orbital satellite photos of the crater floor right now and clearly see a massive, dried up, fan-shaped expanse of sediment sitting right on the surface.
Yep.
Geologists call it the Western Delta. It is highly visible, structurally obvious, and to be honest, it is the entire reason NASA spent billions of dollars to send Perseverance to that exact set of coordinates.
It was the prime target.
The logic was simple. There is a highly visible river delta on the surface, so let's land a rover on it and study the dirt.
Right, because the assumption was that the visible Western Delta represented the primary and perhaps the only significant period of aqueous activity in that region.
That was the lake.
That was the lake, that was the event. But the RIME-FX data revealed that the newly discovered cliniforms are situated deep beneath the crater floor. They entirely predate the formation of the visible Western Delta.
It's underneath it.
The buried delta is completely physically separate, structurally distinct, and vastly older.
Which fundamentally changes the narrative of the expedition. I mean, imagine organizing a massive, multi-million-dollar archaeological dig here on Earth.
Okay.
You travel to a remote desert to study a famous, beautifully preserved ruined city that just sits right there on the surface.
Right, you can see the walls.
Yeah, and you spend months mapping the visible streets and analyzing the standing architecture. But one day, you decide to run a radar scan 100 feet straight down beneath the central plaza.
Just to see.
Just to see. And you discover an entirely different, vastly older, completely unknown civilization buried directly beneath the one you came to study.
Oh, that's exactly what this is like. It forces you to rewrite the entire history of the region.
You have to start over.
Pretty much. On a planetary scale, the presence of an older, distinct subsurface delta means that massive volumes of water were actively flowing into the Jezero Basin much, much earlier in Mars's history than any previous geological models had predicted.
It wasn't just a one-time thing.
No, the hydrological life cycle of the planet was far more complex. It featured multiple distinct periods of massive water flow, and it originated much closer to the initial formation of the solar system than the surface features alone ever indicated.
Now, discovering an older, hidden era of flowing water is obviously thrilling for the geologists mapping the rocks.
They're ecstatic.
But for you, the listener, trying to understand the larger context of space exploration, we have to answer the ultimate question here. So what?
The big so what?
Yeah. Why does it matter to us if water was flowing on Mars 3.5 billion years ago versus 4.2 billion years ago? Why care about that gap?
Right.
Because NASA didn't send Perseverance to Mars just to map the plumbing history of an empty crater. The ultimate overarching directive of the mission is to search for the chemical or fossilized signatures of ancient extraterrestrial life.
And the difference of a few 100 million years is exactly what dictates the probability of life emerging.
Okay, walk us through that.
We have to look closely at the primary stated conclusion from Emily Cardarelli's research team. In their paper, again published in Science Advances, they state their findings very clearly.
What did they say?
They wrote, RIME-FX has revealed an earlier subsurface deltaic environment under the present-day delta, thereby extending the period of potential habitability for Jezero back further in time.
Extending the period of potential habitability.
Yeah.
That phrase right there is the crux of this entire discussion. It is entirely about widening the window of opportunity.
Exactly. And to truly grasp why an extended window of habitability is such a monumental finding, we have to kind of zoom out from the Martian surface.
Look at the big picture.
Look at the broader context of what astrobiologists are discovering across the rest of our solar system right now, because we are currently living in an unprecedented golden age of cosmic chemistry.
We really are. While Perseverance is pinging radar into the dirt on Mars, other international space missions are returning absolutely mind-bending data from the deepest, coldest regions of space.
It's happening everywhere.
Look at the Hayabusa 2 mission, right? It traveled to the near-Earth asteroid Ryugu, actually collected physical samples from its surface, and successfully returned them to Earth for laboratory analysis.
Which is still just unbelievable to me.
And when biochemists analyzed those pristine space rocks, they didn't just find dead minerals.
No, they did not.
They found actual, complex, organic building blocks necessary for DNA and RNA.
Yeah, among the compounds identified in the Ryugu samples was uracil.
Uracil.
And uracil is not just some random carbon molecule. It is one of the 4 essential nucleobases that make up the structure of RNA, literally all living organisms on Earth.
Including us.
Including us. Finding an intact nucleobase embedded within a carbonaceous asteroid, just drifting through the freezing vacuum of space, it is a staggering confirmation of our chemical origins.
And it isn't just asteroids either. Astronomers using advanced spectroscopy have detected vast clouds of colliding cosmic dust.
Yeah.
Carbon-coated grains just drifting through interstellar space. And the physical friction and radiation interacting with these complex carbon grains, it provides the exact kind of early, raw chemical energy and complex organic molecules that serve as the prerequisite sparks for biological life.
The universe is practically overflowing with the ingredients.
Which forces a massive synthesis of our current data. Like, we now have empirical physical proof that the fundamental building blocks of life, the complex amino amino acids, the RNA nucleobases like uracil, and the energetic carbon compounds are demonstrably floating throughout our entire solar system.
They're not unique to Earth at all.
They are constantly being distributed by comets, meteorites, and cosmic dust. The seeds of life are essentially everywhere, just drifting in the dark.
But, and this is a massive but, a seed is entirely useless without a crucible.
Without soil.
Right. An RNA nucleobase cannot transition from complex chemistry into actual replicating biology while it's just sitting on the surface of a frozen, radiation-blasted asteroid.
Right, there's no atmosphere.
No atmosphere and no liquid solvent to facilitate chemical reactions.
Yeah.
The missing variable in the equation of life within our solar system is not the availability of the chemical ingredients.
It's the environment.
It is the availability of an incubator. You need a highly stable, long-lasting, protected environment where those cosmic ingredients can land, dissolve into a solvent, mix together, react energetically, and basically be given the millions of years necessary to slowly evolve across the threshold into biology.
An incubator like, I don't know, a stable, deep-water lake fed by a churning, mineral-rich river.
Exactly.
A massive delta system slowly depositing nutrient-rich mud and sand over millions of uninterrupted years, shielding the fragile chemistry from solar radiation.
You nailed it. By proving that Jezero Crater contained a massive, dynamic, flowing water system, a protected lake, and a prograding river delta hundreds of millions of years earlier than we previously established. The Ramifax data vastly expands the target area.
It gives it more time.
Yes, the window of opportunity for those ubiquitous cosmic seeds to safely take root on the Martian surface just got incredibly wider.
Because it fundamentally comes down to statistics and probability, right?
It's a numbers game.
If the lake only existed for a brief geological moment, say just a few thousand years, the mathematical chance of a meteorite carrying the exact right amino acids splashing down into the right mineral-rich pond at the exact right time is, well, it's infinitesimally small.
Almost zero.
But if that stable, aqueous environment existed for tens or even hundreds of millions of years, the probability of the right cosmic ingredients finding their way into the incubator goes up exponentially.
And that's why a functioning, stable river delta existing between 3.7 and 4.2 billion years ago is the critical data point here.
The timeline aligns.
It perfectly aligns. That specific time frame places the presence of a vast, stable water cycle on Mars perfectly synchronous with the exact period in history when we know biological life was first beginning to miraculously emerge from the primordial oceans here on Earth.
Which naturally leads to a massive, just deeply philosophical question that I want you, the listener, to really sit with for a moment.
It's a heavy one.
It really is. We have planet Earth, a rocky world within the habitable zone that clearly possessed the right environment to brew biological life 4 billion years ago.
You know that for sure.
And now, thanks to ground-penetrating radar, we have empirical proof that Mars possessed a remarkably similar, highly stable, watery environment at the exact same time in the solar system's chaotic history.
Right next door.
So, does this imply that life actually originated independently on Mars, sparking into existence through a completely separate parallel genesis?
Just a second tree of life.
Yeah. Or does it suggest that early Mars was simply a perfectly primed, watery incubator that caught the exact same drifting cosmic building blocks that seeded Earth, but for whatever tragic geological reason, the Martian fire just eventually went out?
That dichotomy represents the ultimate driving question of all astrobiology.
It really does.
And the truly beautiful aspect of this moment in scientific history is that we are no longer confined to merely philosophizing about it in theoretical papers.
We're out there.
We currently have a 1-ton nuclear-powered rover physically parked on top of a 4-billion-year-old incubator, actively taking core samples right now.
Which is mind-blowing.
It is. The realization that planets we previously categorized as long-dead worlds can successfully hide their ancient, habitable pasts deep beneath an irradiated crust.
Yeah.
It completely reframes how we must approach the exploration of the rest of the universe.
Which brings us perfectly to the cosmic perspective of all this, because we are not spending billions of dollars and decades of research merely to map one crater on one neighboring rock.
No, this is much bigger than Mars.
Exactly. The operational techniques we are actively testing right now in the Jezero Basin, with deploying ground-penetrating radar on alien terrain, building high-resolution 3D subsurface topographies from orbital and rover data, and successfully hunting for hidden ancient hydrological systems. These are not just one-off science experiments. They are the rigorous practice rounds.
They form the methodological foundation for the future of interstellar exploration.
We're learning how to do it.
Exactly. Astrobiologists and astronomers have already utilized advanced space telescopes to identify at least 45 distinct Earth-like exoplanets located outside our solar system.
45 of them.
And they present tantalizing targets for atmospheric and eventually physical exploration. It represents a real-life, multi-generational Project Hail Mary.
Just reaching out into the dark.
We are peering across light years at these distant rocky worlds and frantically trying to build the tool sets required to determine if they actually harbor life.
But the harsh reality of space exploration is that it is incredibly hostile, it is prone to catastrophic failure, and it is utterly unforgiving of poor engineering.
You only get one shot most of the time.
Right, and we are constantly reminded of the chaos of the cosmos. Just look at what happened recently when NASA's Hubble telescope unexpectedly caught a massive comet violently breaking apart.
Oh, I remember that.
It just shattered into pieces in real time as it approached the sun. The universe is incredibly destructive.
It really is.
Or consider the absolute logistical miracle when the European Space Agency managed to reestablish a connection with a lost spacecraft that had been spinning silently in the void, completely unresponsive, for months.
Everyone assumed the mission was a total loss.
A complete write-off. But things go wrong in the vacuum of space constantly.
And the unforgiving nature of the cosmos is precisely why the overwhelming success of the Ariane-PAC's instrument on Perseverance is so vital to our long-term goals.
It proves the concept works.
Exactly. When we eventually develop the technology to send probes to investigate those 45 other Earth-like exoplanets, we cannot simply look at their visible surfaces and assume we are seeing an accurate historical record of their habitability.
Because space is too chaotic.
Atmospheres get stripped away by stellar winds, surfaces get sterilized by gamma-ray bursts, and oceans boil off or freeze solid.
So the surface lies.
The surface lies. By successfully utilizing ground-penetrating radar on Mars to locate an ancient, buried zone of habitability that was completely invisible from the surface, we are rigorously stress-testing the exact remote sensing methodologies we will inevitably require when investigating those distant worlds.
Mars essentially serves as our local, highly accessible laboratory for understanding complex planetary evolution. It is our ultimate training ground.
It is. Because if humanity hopes to eventually understand the incredibly complex mechanisms of how an entire planet transitions from a vibrant, habitable oasis into a barren, uninhabitable wasteland.
Which we really need to know.
We do. Or if we want to learn how to effectively detect the hidden chemical signatures of past life buried beneath an alien crust, we have to perfect our sensory techniques somewhere.
We can't practice on an exoplanet.
Right. Mars is close enough that we can afford to send robotic proxies equipped with experimental radar to practice reading the deeply buried geological record.
We are essentially taking our technological baby steps inside Jezero Crater.
Very expensive baby steps.
Very expensive, yes. But think about the sheer audacity of what has been accomplished here. We launched a robotic laboratory millions of miles across the freezing void of space.
Yeah.
We successfully landed it inside a 45-kilometer-wide impact scar. We commanded it to ping the solid ground 35 meters deep with invisible radio waves.
It sounds like science fiction.
And by meticulously analyzing the timing of the echoes bouncing off different densities of rock, human beings successfully read the physical diary of an alien planet from 4.2 billion years ago.
It's astounding.
If we can successfully execute that level of remote archaeological science right next door, we are actively writing the technical instruction manual for exploring the rest of the galaxy.
And the findings validate our entire theoretical approach.
Yeah.
I mean, astrobiologists hypothesized that investigating the deep subsurface was the only viable method to locate older, perfectly preserved, habitable environments on heavily weathered planets.
They guessed right.
The exhaustive data published in Science Advances proves that hypothesis was entirely correct. The deeply buried delta absolutely exists. The timeline of flowing Martian water has been radically extended.
Yeah.
And the historical window for life to have potentially taken root is much wider than we ever dared to hope.
So let's just take a breath and recap the incredible arc of the journey we've just been on.
There's been a lot of ground to cover.
It really has. We started by looking at a 45-kilometer-wide impact crater, just an unfathomably violent scar left over from the chaotic early days of the solar system.
Right.
We looked closely at the inner walls of that crater and identified a distinct bathtub ring of precipitated carbonates that strongly hinted at the presence of a massive, ancient, stable lake.
The chemical memory.
The chemical memory, right. Then we followed the path of the Perseverance rover as it executed 78 distinct traverses across the red dust, utilizing the REMA-FAX radar instrument to peer 35 meters straight down into the planetary crust.
And down in that impenetrable darkness, the radar data revealed the unmistakable geometric architecture of clinoforms.
The sloping ramps.
The distinct sloping sediment layers that can only be formed by the fluid dynamics of a massive river delta emptying into a stable body of water.
Yeah.
A delta that the dating models suggest formed up to 4.2 billion years ago, which completely rewrites the established chronological timeline of Martian water. It pushes the window of potential chemical habitability far deeper into the planet's past.
It is a truly stunning piece of interplanetary detective work.
Best in a generation.
Truly. We've proven the water was there, and we've proven it was there exactly when the cosmic seeds of life were heavily bombarding the inner solar system. But as we wrap up this exploration, there's one final lingering concept I really want to pose.
Oh, okay.
A thought based purely on the stark contrast between the geology of Earth and the geology of Mars.
Ah, yes. The critical difference lies in how the two planets managed their crusts over billions of years.
Exactly.
We know that here on Earth, our planet's geological history is incredibly dynamic and ultimately, well, it's destructive.
It eats itself.
It does. Our planet possesses an active system of shifting tectonic plates. The terrestrial crust is constantly moving, grinding, subducting deep into the mantle, melting down into magma, and then being reformed.
Earth is essentially a massive recycling machine.
Exactly. Earth aggressively recycles its own crust, and in doing so, it relentlessly destroys its own ancient geological records.
Which is frustrating for geologists.
It is incredibly difficult for geologists to locate a pristine, untouched rock formation on Earth that is a true 4 billion years old, because the planet's tectonic activity has crushed, folded, and melted the majority of the early crust over and over again.
So the evidence is gone.
The evidence of our earliest biological history has largely been erased in the planetary furnace.
But the geology of Mars is fundamentally different. Mars is relatively still.
It is.
It cooled down faster, and it does not possess that active, destructive tectonic recycling system. The crust locked into place billions of years ago. And that reality leads to a truly provocative thought. If a fragile geological structure like a river delta constructed entirely out of loose sand, silt, and mud, deposited 4.2 billion years ago, if that is sitting there, structurally intact and perfectly preserved in the dark, 35 meters beneath the floor of Jezero Crater, what else is waiting down there?
It forces a chilling realization, doesn't it?
It gives me goosebumps.
If the delicate structural architecture of a riverbed can survive completely intact for over 4 eons, simply because the planet's crust stopped moving and locked it safely away from the surface radiation,
Yeah.
we have to ask what other delicate ancient secrets are sitting perfectly frozen under the dust.
Right.
The deep Martian subsurface isn't just a geological vault. It could be the most pristine biological museum in the entire solar system.
Just waiting for us.
It is entirely possible that the very chemical fossils of early life, the actual undisturbed biological remnants of those drifting cosmic seeds finally taking root in an ancient lake.
Oh.
They're waiting down there right now.
Oh.
They could be completely untouched by time or tectonic fire, resting silently in the absolute dark, just waiting for us to ping them with a radar.